people have wondered about infinity for thousands of years. We're going to continue that tradition of thinking about infinity, but we're going to focus in on one specific instance of infinity in mathematics. What does it mean to say that the limit of a function equals infinity? Here's what it means. The limit of f of x as x approaches a equals infinity means that f of x is as large as you like, provided x is close enough to a. Now, as a bit of a warning, I'm not saying that this number, limit f of x, x approaches a, is equal to this number. Infinity is not a number. What I am doing here is attaching a precise meaning to the entire statement that the limit of f of x is infinity. So that's what it means precisely, but what does that mean practically? Let's go to the board. Here's an example. The limit of 1 over x squared as x approaches 0. Now this limit is not equal to a number. 1 over x squared is not getting close to a number when x is approaching 0. But 1 over x squared is as big as I want it to be if I'm willing to put x close enough to 0. For instance, if x is within 1,000th of 0, what happens? Well, to say that x is within 1,000th of 0 is to say that x is between minus 0.001 and 0.001. Now, x is also non-zero here because I don't want to divide by 0. So I've got a non-zero number within 1,000th of 0. What does that mean about x squared? Well, that means that x squared it's bigger than 0, because if I square any non-zero number, it's positive. And it's less than a millionth. So if I take a number within 1,000th of 0 and I square it, now it's within a millionth of 0. And what does that mean about 1 over x squared? Well, if x squared is within a millionth of 0, 1 over x squared is now bigger than a million. What happened, right? I made 1 over x squared very large by making x close enough but not equal to 0. And there's nothing particularly special about these numbers. If I wanted 1 over x squared to be bigger than a trillion, I would just need x to be within a millionth of 0. Now, this example's at once maybe too complicated because I've got some explicit numbers in here, and maybe this formula is not complicated enough to really get a sense of what's going on. Let's look at a slightly more complicated function. So what's the limit of x plus 2 over x squared minus 2x plus 1 as x approaches 1? Now this is the limit of a quotient. So your first temptation is to think the limit of a quotient is the quotient of the limits. But what's the limit of the denominator? The denominator is a polynomial, and polynomials are continuous. So I can evaluate the limit of the denominator just by plugging in 1. And if I plug in 1, I get 1 minus 2 plus 1. That's 0. The limit of the denominator is 0, so I can't simply say that the limit of the quotient is the quotient of the limits in this case because the limit of the denominator is 0. And that limit law doesn't apply in this case. What am I going to do? Well, I could also notice that the denominator factors. X squared minus 2x plus 1, I can rewrite that. X squared minus 2x plus 1 is x minus 1 squared. So instead of evaluating this limit, I could try to look at this limit, the limit of x plus 2 over x minus 1 squared as x approaches 1. Now what do I know? The numerator is x plus 2, and if x is close to 1, I can make x plus 2 close to 3. What about the denominator? A number close to 1 minus 1 squared is a number close to 0. But not just a number close to 0. It's a positive number close to 0. So let me write this down. Right? The numerator is about 3, and the denominator is about what? Well, it's some small but positive number. And what happens if I take a number like near 3 and divide it by a number which is small and positive? That number can be as big as I like. So I can make this quantity as large as I like if I make x close enough to 1. Because I can make the numerator close to 3 and I can make the denominator as close to 0 and positive as I like. And if I take a number close to 3 and divide it by a number close to 0, I can make a number as large as I want. So this limit is equal to infinity. The homework includes even trickier situations. For instance, limit problems where x approaches negative infinity instead of infinity. If you get stuck, I encourage you to contact us. We're here to help you.